Please like and leave a heart. Please.
There we go. Hello, everyone, and welcome to the show. This is the Vidor Locksmith Show, and I'm your host, David Gibson, where we are unlocking the secrets to success in the oil and gas industry, one interview, one technical presentation, and one technical screw up at a time. So please, guys, let me know if we find the technical screw up for the day or multiple. You never know what's going to happen here on the show. So glad you guys are here with us. Obviously, today is Friday. It's 10 a.m. Another time for another great show. I'm really excited about today's show because this is a topic that I think a lot of us know at least a little bit about, but there's a lot that goes into designing drill bits, and today's a great chance to be able to learn about just that. So guys, let me know where you're watching from. Love to be able to give you guys a shout out here on the show. And also extremely big news, and I am very appreciative and thankful today we have a new sponsor. So our new sponsor is KEYDRILL. So special thanks to the guys from KEYDRILL for taking part in this and helping to be able to support the show, to be able to continue bringing educational content out there for everybody in the entire industry to be able to see. So special thanks to those guys. Like I said, give us a shout out here on the show. Love to be able to let everybody know who's watching, put you guys up here on the screen. So let's run through some. Where is it? Okay. Well, StreamYard has lost access to your LinkedIn account, David Gibson. Don't worry, we've got you covered. Reconnect your destination here. Are you guys still watching on LinkedIn?
I am.
Is it still working?
Yes.
Huh. That's kind of an odd message to get in the middle of the show. It would have been nice to have that beforehand, but if everything's still working, we'll keep going. So, all right, I will take care of that after the show. All right, like I said, let's give shout outs to some people here. Maybe that's the technical difficulty that we're going to have today. I don't know. If it just cuts out halfway through, just let everybody know. You guys can watch on Facebook and or YouTube. We stream live on all three platforms at the same time, all the time. And if you ever want to go back and watch a show, I know it's not always the best to be able to try finding stuff on LinkedIn. So you can go and watch them on YouTube. It's a little bit easier to be able to find the content and kind of move around. You won't be able to get all of the comments and stuff that are usually there, but it's usually a pretty good destination to be able to go and check stuff out, right? Like I said, guys, let me know where you guys are watching from. As always, we got Mr. John DeWart tuning in this time from Elkhart Lake, Wisconsin. Thank you, sir. Jeff Chutton says TGIF. Yes, sir. Do agree. Eric tuning in from sunny south of France. And like I said, the guys from KEYDRILL. Ian, here he is, tuning in from Houston, Texas. Thank you guys so much for supporting the show. Really do appreciate it. Feel honored to be able to have you guys on it as a sponsor for the show. We've got Omar tuning in from Boston. Thanks for being here. This is tuning in from North Dakota. LinkedIn user, good morning from Houston. All right, not sure who it is, but thanks for being here. Andy Wood says good afternoon from the UK. And in a couple of weeks, I don't have my sticky note. Oh, wait, here it is. Hold on. Andy Wood will be October 6th. Andy Wood's going to be our guest October 6th. We're going to be talking about geothermal stuff. So be sure to tune in for that one. Andy, thanks for tuning into the show. Another LinkedIn user says, good morning from Edmonton. Thanks for being here. Hand pink waving, Omar. All right, cool. We'll fly with it. All right, guys. So we've got a quick little commercial break. But before we go there, right, we have some stuff to give away. And this time, it's not hashtag Gibson. It's hashtag KEYDRILL. You got to put in hashtag KEYDRILL to be able to win yourself a bit. Now, right now on hand, all I've got is the drill bit. But I will be sending this drill bit, whoever the winner is, plus some KEYDRILL swag. I'm going to talk them into giving me some KEYDRILL swag, maybe some stickers, hats, I don't know, pens, pencils, whatever it is, free MWD tools, whatever, maybe, a pulsar driver or something like that in that little thing. But put in hashtag KEYDRILL for your chance to be able to win, guys. And here is a quick little video from KEYDRILL.
KEYDRILL is at the forefront of MWD technology. Driven by ongoing research and development, our systems are built to be rugged, modular, and customizable, meeting the specific needs of the industry. This dedication has positioned us as leaders in MWD system design and production.
All right, guys. So we've got a lot of people watching and a lot of people commenting, but we've noticed the technical difficulty. First of all, thank you, KEYDRILL. But the comments from LinkedIn are not coming into the program that I use called StreamYard. So for everybody who just put in hashtag KEYDRILL, I don't know if I'm going to be able to enter you into the thing. So let's do this. So what we're going to have to do is probably just do this throughout the entire show, and just kind of see what happens. So throughout the entire show, keep putting in hashtag KEYDRILL and your questions and comments for our guest today. Special thanks to KEYDRILL for putting this together. We're just going to keep saying their name over and over and over and over again. Here, maybe we might even do this. I'm doing this all on the fly. Nope, that's not what I meant. And hashtag sorry, here we go, doing it on the fly, just like typical oil field stuff. When there we go. Boop, boop, delete, and we'll just leave that. Save. There we go. We'll just leave it running. We can run the show with that. No worries. You guys at KEYDRILL will love it, hopefully. All right, so let me see if any of the comments, if you guys can, if anybody's commenting still from LinkedIn, please, maybe Tracy, if you'll try to throw something in there just to see if it'll pop up on my screen. If it's not, I do want to make sure that we get the questions in, because like I said, this is a really important show. I want to make sure that we're able to get all this stuff. So before we bring our guest on, okay, so yeah. Oh, yeah, it's working again. Okay. So now I'm able to see the LinkedIn comments again. Okay. All right. So without further ado, let me bring in our guest of the day, Vasiliy. Vasiliy, thank you so much for being here, man. I really, really do appreciate it. I know you've been a fan of the show, so it means a lot to me to be able to have you here on the show now.
Thank you very much for having me. I actually can't quite believe that I am on the show. So thank you for having me here.
Well, it's great. So I know your background is drill bits. So for everybody who doesn't know who you are, give us a quick rundown of your background and what you do.
Well, I mean, my background is drill bits, of course. That's a big part of my career, and I worked with some great companies in the past. I started with Schlumberger in drilling and measurements, and was doing all sorts of logging and MWD. So I'm quite familiar with MWD world, and I worked in Caspian Sea and the North Sea with Schlumberger, which is not a big surprise, and was specializing on formation pressure while drilling, which is quite in line with my diploma project, actually. So I'm a reservoir engineer by trade. And then for 10 years, I worked for a great company called National Oil Well Barco in various positions. And my last post was with Reed Hycalog, hence the drill bits. And not only drill bits, it's anything to do around drill bits. So obviously, Reed Hycalog is a very diverse company. And for the last couple of years, we've been building a very ambitious little startup called ZerdaLab, where we do a lot of things in the machine learning space and artificial intelligence, all in relation to drill bit design selection, cutting structure modeling, performance assessment, and so on. And I'm there. I'm still there.
Excellent. Well, take me through the process of what it takes to be able to like what is the starting point for getting the right bit for the right run, the right job, the right area, right? Because I know you like, a bit that works in West Texas isn't going to be the one that works in in Southeast Asia, right? Like,
yeah. So that's a very good question, and there are various approaches actually that are being employed, mostly focused around the historical runs and historical performance assessment of the drill bits, and then iterative approach to improving on what worked and what didn't work. So it's very empirical and based pretty much on the history of the runs, which has some advantages because you have some confirmed performance attributes that you want to see in a drill bit, but also has some disadvantages because it doesn't account for innovation or what's new in the technology of a drill bit. So the drill bit technology is moving at quite high pace, especially on the cutter's front, but also on the design, on CFD, on materials. And if you look at the performance data from historical point of view, I'll take an example. If your offset is from 2015, no matter what it is and how many blades and how many cutters the bit has, it's almost irrelevant to what that performance of the drill bit represents and the condition of the drill bit represents if you apply it to contemporary technology, contemporary cutters, secondary features, and the design by itself. So design of a drill bit.
So you're saying, like if I had a 2015 drill bit, it would just be worthless now.
It will give you a rough idea of what kind of ROPs, rate of penetration, and intervals you were historically achieving. Translating it to how the contemporary bit would work in the same environment is, in many cases, there will be almost no correlation. You can look at the bit in new conditions. So the thing that people and it's very difficult to account for is if the bit is new, right? It gives you a certain performance for the first, 10 runs, 20 meters, 1,000 meters, depending on application. But once bit starts dulling, it's obviously no longer representative. The way the contemporary bit dulls is very different. It's much longer. And the stability features and other important aspects of drill bits like hydraulic performance is designed very differently today. So CFD modeling today, which is hydraulics of a drill bit, is on completely different level, and it takes many more iterations, or the designer would go for many more iterations today to get the most balanced hydraulic performance of a drill bit. And hydraulic is very important because it's not only about cuttings removal, but also cooling the cutters on the shoulder or across the entire face of the bit. And it's heat that actually kills the drill bit. If you take the diamond, if you take the PDC diamond today, right? I mean, you properly cool it, and let's say there is no vibration, and you cut the rock with that, it pretty much will never fail. If you cool it properly, you can drill the application or your section pretty much indefinitely, virtually, because there is nothing harder than this diamond that you drill. Even the hardest rock is not as hard. So what kills the diamond is the temperature fluctuation, which is obviously a byproduct of stick slip or torsional vibration. And so that's pretty much it. So the designer role is to create a stable environment for the drill bit. So and that opens the question: what is primary? What is secondary? Is it design or is it the cutter? So it's both. But if the design is incorrect, it almost doesn't matter how good your cutter is. You will eventually damage it, and the bit will stop drilling.
Wow. It's just funny to think that, like, you know, if I have a 2015 car, there's still a lot of value in it.
Mhm.
But, you know, if it's a drill bit,
Mhm.
it's not quite quite going to be in reference to today's bits. It's not going to be as useful. All right, so now that you've kind of set the priorities there, what's the next step in the design process?
Well, the next, where do I start? There are so many things that are relevant to this question, and
Well, we didn't say the interview
and
was going to be easy.
yeah, no, I'm fine. I'm fine with tough questions, right? So, so the design itself. So there are a couple of aspects. First of all, how accurate the design is, how accurate the prediction of your model of how the cutting structure will behave. That's the first question. Second thing, how many iterations would you do to get the best result? And how good your interpretation of the application is. So, and all of these three aspects need to be developing, and they are developing. So, for example, interpretation of the application properties. There is obviously a lot of geophysical information that is being collected, a lot of properties of the rock and etc. And there is a lot of things are happening in trying to correlate what we see downhole in situ to how the cutting structure behaves. On the drill bit itself, in terms of iterations are difficult, right? So it's a very complex and very heavy process to iterate one feature at a time, or a particular property of the bit at a time. And the future would be in automating iterations. That's probably the first and the most obvious step. So instead of designing, assessing results, and making decision, do you want to do a next iteration? You set the objectives for the design. So you say, I want this torque, I want that point loading on the cutting structure. And point loading is very important. It's probably the most important, in my mind, is the most important property of the cutting structure, is how much pressure we create on each point against the rock that we're trying to fail.
I'm glad you explained it, because I had never even heard that concept before. So that's good to know.
You're welcome. So this what you do, you set up a particular flavor of the cutting structure that you want to achieve, and you let an automation to do iterations until it gets as close as possible to the result. So all the automation and all the machine learning, so that's where machine learning comes into play, and artificial intelligence in that sense, when it comes to drill bits, is not to replace the decision making of an engineer or an expert, but to help to get the answers that the engineer is trying to make to select the right cutting structure. So automated iterations is probably the first. The model, every model has the error model within it, and more layers you put on top of each other, wider the error becomes. That's why it's very difficult to correlate the actual bit performance, because it's also very difficult to isolate the drill bit from the rest of the system. But the error, the total error at the model is making it almost an unachievable task to get the direct correlation. So therefore, there is a lot of lab testing going on with the cutting structure. But and the last part, that what modeling does not account for, is the worn state of the cutting structure. So at what stage it will start wearing, where it will start wearing, and how the dynamics of the drill bit will be affected. So implications of being able to do that go far beyond the design. It goes into all the way to operations, right? If you know how the bit behavior changes with the cutting structure wearing, you can actually make some operational decisions based on that. And only if there is a strong correlation and error model is very narrow. I hope that's
I mean,
yeah. Sounds a bit heavy.
There's so much to it. I've never been involved in this process, and prior to doing, anything with machine learning or artificial intelligence, what would you say is the normal timeline of being able to take a bit and do these iterative changes? Just to be able to go through one iterative change, what would that normal time span be like versus what it is now or potentially in the future?
Well, it depends on how well-known application is and how much data you have and the quality of the data. So data collection is very important as well. That's on the back end of the design, and I hope we'll touch on that a little bit during the show. But yeah, depending on the quality of the data and how powerful the machine is, well, that's secondary probably. I would say to iterate on a drill bit, it can be anything from a couple of days to a couple of weeks, depending on the complexity of what you want to achieve. So if you're only changing some minor aspects of the drill bit cutting structure, mainly not touching the primary cutting structure, let's say you're happy with what you see, that can be quite quick. So if we're talking about any changes to the tip profile, which is the shape of the drill bit, then it's pretty much new design. If you then have to redo the CFD, which is hydraulics of a drill bit, so it's a computational flow dynamics. Computational flow dynamics actually takes probably most of the time, and it should be, because the hydraulics of the bit is probably as important, if not more important, than the cutting structure itself, and it's very commonly being not emphasized on. So I think the cooling of the bit and removing the cuttings is as important as should be really the cornerstone of the bit design. So
why do you think that is? Why is that not being pushed harder? Why is that not a bigger concern for more people?
Well, it is pushed by the bit designers. So every drill bit company you will talk to, they will say how important the CFD is, but that's not what comes across as a conversation point with the customers. I think customers and the end users of drill bits, the most important is, what kind of depth of cut I'm going to achieve with this bit, what kind of ROP, how long the bit is going to last. And CFD is being talked about and the hydraulics of the bit, but almost I feel like, a secondary to the main conversation. So this is just not coming as strong in probably a marketing of the cutting structure, but it is being taken seriously. Again, it's a very complex process. It's a very highly skilled thing to do. And sometimes rule of thumbs are used for some of the bit designs, which I'm not a big fan of generally using rule of thumbs, but it is a shortcut in a way. But yeah, CFD is as important, and perhaps it needs to be point of conversation. At least if you are in a position to select a drill bit for your application, please make sure you demand this to be provided to you and explained as well, because it's a lot of nice colorful pictures, right? But what they actually mean represents certain aspects of a drill bit, and you can then look at two different drill bits with a different set of eyes, right? If you remove the cutting structure from a conversation just for a moment and just focus on the hydraulic performance and try to understand the differences between two, I think you will do yourself a lot of favors.
So if I was in the position to be able to purchase a bit, and I should be asking to see the CFD analysis and have it explained to me, what are some of the questions I should be asking about it to the vendor?
Well, again, it's what we try to achieve with the design is to ensure that there is no recirculation or minimal recirculation of the fluid. Make sure that there is no dead zones i.e. where the fluid is not getting to. Make sure what measures were taken to reduce the erosion of a drill bit, especially on top of the blades, because that's where the cutter sits. And brazing is not really keen on erosion. So brazing is actually very susceptible to erosion. So that's the things that you want to look at. So recirculation, shear velocity should be very balanced. The flow need to be distributed proportionally between the blades, depending on the volume of cuttings that each blade removes. Believe me, when you will see bad CFD, you will know. It's almost jumps into your face once it is explained to you what CFD represents.
Well, hopefully you'll make a post this next week on LinkedIn. I want to see a picture of bad CFD.
Okay, well, that's easily done. Bad CFD is easily done, by the way.
Yeah, I want to see a picture of like bad CFD, and then maybe a side by side of like good CFD or something like that. You got to do that for me on LinkedIn this next week.
So we have
Go ahead.
No, so we actually have we in our slides we actually use an optimized CFD versus a default CFD, if you see what I mean. So that's how we put things based on rule of thumbs, and that's the optimized one. So I'm not saying the rule of thumbs is particularly bad, but it's not as optimized as it could have been. But we can produce a bad CFD for you. So I hope Rob is on the call today.
I could probably produce a bad one too. I'll just get out some crayons and just start drawing on my drill bit, and then like there's your CFD.
That will do. Yeah. Send us your beat. By the way, we see if we can optimize yours.
Oh, that will be done. That will be done. All right. So let's stay on that same topic. What are other questions? You know, we have the question. I'm the one purchasing the bit, and I say, hey, I want you to explain to me about the CFD. What's good? What's bad? What are some of the other questions I should be asking in general about the bit before I, put it down hole and agree to running it?
I think the set of questions will probably differ from application to application because, so for example, there is a set of very soft applications in Asia Pacific, very soft, and the direction response of a drill bit without any aid, i.e. rotary steerable system, is quite important. So the common questions people ask, what is the tendency of the drill bit to steer or by itself, right? So will it deviate? And there are several aspects in the design that you can demonstrate to show that tendency. And there are also several things that you can do to a cutting structure to either reduce that or to increase that. So in terms of some other applications, so for example, we kind of focus a lot on hard rock because we work with geothermal space, and volcanics are not nice things to drill, especially when your fluid is not your ideal mud, and the flow rate is normal. So you do all the great work on CFD, and then you have to adapt to what is available to you. So you would, of course, look at the stability of the drill bit. So ROP is not a primary question. I think the stability of the bit is the primary question, and stability characterized by different companies in a different way. So there is a net lateral force calculations or out of balance force calculations. Gauge length comes into play, which defines some of the stability properties. But one thing to understand about bit stability is calculated for the cutting structure embedded into the rock for a predefined depth of cut, and then it's rotated, and then forces applied to it, and pretty much the resultant forces are being calculated. So the stability of the bit as designed is only valid for not non-dulled bit. So once you start dulling, your stability is out of the question. So that's why it's very important to delay dulling of a drill bit, and that's where the cutters grade and the cooling of the cutters comes into play. The conversation again should not. Let me backtrack a little bit. Conversation is always, or very often, is about blade count and cutter size and etc. So and it shouldn't be. It should be about the stability of the bit and ability of the cutting structure to sustain its condition for a prolonged period of time. Just to put it into perspective, right? So we've designed a cutting structure for test to drill granite. If you take all the usual rule of thumb and all the offset of that granite drilling in the past, it was always kind of heavy set bits, and usually people would say, yeah, we need a heavy set bit. It's granite. It's, 35 plus kpsi compressive strength, really hard, very brittle. But we looked at it from a different perspective. We said, okay, it's 35 kpsi granite, and we need to drill it somehow, and we need to make sure the bit is stable, and we know the bit is only stable when it's actually embedded into the rock. So we need to achieve the state where the bit is embedded. What weight on bit we have available to us? So that was on a test, and they said it was only 2 tons, right? So 2 tons weight on bit on a 6-inch bit body against 35 kpsi rock. So we said, okay, well, we need to achieve a point loading on each cutter that exceeds that compressive strength of the rock. Only then we will be able to fail it. So we ended up with a very defined number of cutters. And if you look at number of blades that were required to put these cutters on, because the blades are there just to carry cutters pretty much, right? To define the cutting structure. So it ended up to be a 5-bladed bit. And when you look at it, well, that's so different from what the offset tells us and what experience tells us on drilling the rock. So we then tested that bit in that granite against a common offset bit, and it drilled 2.6 times faster, and it came out without a single chipped cutter. It was a short test, 10 minutes test, but the offset bit was trashed, right? So, and that's 2 points, right? Performance and the stability. So, and
Wow.
So that's just an example of sometimes preconceived ideas can be quite dangerous, but also the offset does not reflect what is possible today with the cutter technology, with the design methodology, with all the hydraulics and etc. So I think that's a good example. So going back to the question, what questions you should ask is this bit stable? Will I achieve a stable state of this drill bit with the weight on bit and RPM that is available to me? That's why it's very important for designer to know what your intentions are, because it's your intentions are pretty much a representation of your limitations. What kind of BHA you are running, how deep the well is, what the buoyancy factor is, the rig capacity, and etc. So you really need to know what your limits are and design the cutting structure to stay within those limits, but to try to get the maximum performance possible.
So I want to touch on something that you mentioned there, which was the weight on bit available, right?
Mm-hmm.
And that leads to me thinking, making sure that and I'm see how I frame this as a question, but like, how much of what you're doing also in delivering the bit design and everything also includes the training or the information to the driller to say, hey, look, don't put 1,000 on it. It needs the full 2,000 on it, as far as the weight on bit, or the 2 tons you're saying. Like it needs all of that to be able to make sure that it's engaged and it's drilling properly. So is that something else that myself as the purchaser should be saying, like, hey, what else do we need to know, or what training do we need to be able to make sure that we're doing this correctly? Because I'm guessing, and you can touch on this as well, that you've designed bits over your career that were ideal for the situation, but then were applied incorrectly at the rig site.
Mm-hmm. That's a very good question. So first of all, just to clarify, I'm not a bit designer. I haven't designed a single bit in my life.
Oh,
so,
okay, okay.
But I work with bit designers, right? So
Yes.
So I'm a bridge between the operations and a designer to make sure the information quality is there, the communication is there, right? So I haven't designed a bit. I influenced several designs and maybe conceptually looked at what's important from operation perspective, because that aspect can elude a bit designer as well, right? So some of the limitations might not be very clear of why certain things done in a certain way, but the training is quite important to a driller. The driller should really understand what bit they're putting at the end of the BHA and for what purpose. So a lot of this information is carried out in the spec sheet. Project on the background to really look at what is important on a spec sheet, what information is important, and things like a minimum weight on bit for a given environment is probably quite important as well. But different application can dictate different minimum weight on bit. So i.e. you want to achieve a particular depth of cut, so you need to drill with a minimum ROP of something to ensure that stable state. But the spec sheets will change in the future, the way the information is communicated. And it's probably the easiest way to give some information to a driller or to drilling engineer, to whoever is responsible for a drilling phase of operations. It's the one that they always will have. Nobody has time to read 25 pages manual or to a case study of the SPE library, unless you really are in trouble and need to do a research, but you usually call kind of people and do online research. So that's why it needs to be very concise and very to the point. Another thing you do as a designer from a bit perspective, you obviously try to protect the drill bit from all eventualities. It's not always possible, but yeah, so certain things need to be part of a training. Yeah.
Okay. Well, we've got a handful of questions that I want to be able to get to, but then I also know you wanted to be able to talk about data collection and how that relates to the drill bit. You said mentioned that earlier, and you wanted to make sure we get to that. So I wanted to be able to cue you up for that one. What do you want to be able to talk about there?
So data collection, again, if you look at how the bits were designed historically, which we touched on here already, so it's highly iterative process based on the offset performance. So it relies on this data to be collected properly and communicated properly. So if I put today 10 people in front of a drill bit which is dulled, you will probably get 10 different dull grades of a drill bit, because people rely on their experience and their interpretation of a dull, and people have different experience, right, and different expertise level on the subject. So the data collection should be objectified a little bit more, or made more objective. And today, we are living in 21st century. Computer vision is a very mature technology today, and a lot of companies already started trying to adopt computer vision to really standardize the data collection. But you do data collection to improve your design and to understand the performance of a drill bit, but you also do that to see if you can calibrate the condition that you see that's in the future, condition of the bit that you see to the model that you use to actually to design the bit in the first place. So, and you close the loop by doing that. So yeah, another problem with data collection currently is actually there is a lot of copy paste. So from one system to another, to another, to another. So, and a lot of things being kind of being lost in translation sometimes. And the data collection need to be made so simple. The simplicity will ensure the volume. And the collected data should actually provide you with an answer and with aid to understand your bit performance. So you're not collecting the data for the sake of collecting the data, but to help yourself to write a report, for example, as an output of that data collection. So that's why it is important. And I'm pretty sure within a year or two, couple of years, it will this approach will start maturing and will become kind of pretty much standardized way of collecting the data.
Well, I know that there is I think it's an IADC subgroup. I think it's the dual bit grading group. And I know that they've been putting a lot of work into being able to automate that. Do you have any idea where that's at right now?
So we are following what this group does. It's obviously a group of experts that tries to, I mean, their objective is, of course, to improve the data collection, but also to maybe simplify the data collection. So there are several, there is a new DAL grading manual that is produced. It's more about classification of the DAL and how you interpret certain condition of the cutter. It's focusing on the cutter and reclassifies the areas on the cutting structure. So considering that the original DAL grading manual took time to implement, this probably will take time until it translates to actual field use. But ultimately, if you collect the information automatically for each cutter on a cutting structure, but also try to train the model to understand different patterns of the DAL and to interpret those patterns. Because, I mean, naked eye, you might not see certain things. Even if you're experienced a drill bit engineer, you might not notice certain things, but that's the beauty of objective computer vision based DAL collection. So that's what's important, is to be able to actually to build the pattern and to interpret that pattern, rather than individual cutter by cutter collection. And you need to ask yourself, why are you collecting this information? Is that to improve the design, or is that to write a report, or is that to improve the drilling performance, your understanding of drilling dysfunction that this bit was exposed to? So those are different objectives, but the data collection need to be standardized to cater to both, to improve the design, but also to write a report and to give the engineer some tips on what is actually happening with the drill bit and what to do next.
Excellent. Clean data always helps out. All right, I want to before I miss them all, I want to start getting in here to some of the questions. So this one's from Jose. He says, when is the right time to change the bit while drilling?
That's a very good question. That's pretty much a headache of every drill bit engineer and driller and etc. So it's a question of economics. For me, as a drill bit, no, I'm not a drill bit designer. As a drill bit associated person, right? So, but for a drill bit designer, it's important to preserve the evidence of the DAL. So, i.e., if the bit starts ringing out, you lose a lot of evidence, and you don't gain much in terms of additional interval. So the time between 0 to 1 is that long. The time between 1 to 2 is much shorter. The time between 4 and full ring out is in a right application is minutes sometimes, right? And in that minutes you will not really gain much in terms of economics of this bit run. So it's, for me, as a biased person, it's always more important to preserve some evidence rather than get an additional meter. In some exceptional cases, let's say if I have 10 meters left to drill for my to reach my geological target, would I trip from 5,000 meters? When this bit is still drilling, not 10 meters an hour, maybe a meter an hour, but I only have to survive for 10 meters. So if the ROP dropped that drastically, tenfold without change of lithology, it will not last for 10 hours, highly likely. But my advice is to get in touch with the vendor of this drill bit, give them as much information as possible, and they will be able to tell you if the bit is actually still any good, and if you can achieve that another 10 meters. Because in pursuit of that extra 10 meters, there are a lot of things that can happen, because as I mentioned to you, the bit which is dulled is not as stable, and unstable bit drives a lot of instability and a lot of dysfunctions elsewhere in the string. So, it's not the bit, but something else can fail in the process as well. So trip out as soon as possible. as soon as ROP drops and you did all your checks, consulted with the vendor, preserve the evidence, pick up a fresh bit. You will gain what you've lost very quickly with a fresh bit.
All right. This one's from Brian. Can an existing bit designed be verified with the model?
That's the objective. That's the objective. So it's not exactly there yet. You can take. So if the question is, can I take a retrospective a cutting structure that I've designed, put it into the new model and see what it does? Oh, of course you can. Yeah, it can be done. You can take a cutting structure and import it into a new model and see how different it is from what originally the design intent was. So that is possible.
Okay, another one back from Jose. In the display of how the bit is drilling and beside the gamma ray bit site, what other curves do you think to add in the chart for a better understanding of how the bit is drilling?
Okay, so there is a lot of things you can add. So gamma ray, of course, is for your if you're still in the same lithology or not. Be wary about gamma ray because usually it is off the bit by, if you're lucky, maybe by a couple of foot. If it's a conventional MWD, probably 10 meters or so. So keep that in mind. But for me, the important curve is weight on bit, torque, RPM. Torque, you need to look at the character change of the torque rather than the value. If the torque all of a sudden is different, it's the magnitude of fluctuation changes, or something in the character changes, that's a good indication. But don't judge it too fast, because it can be just bit balled up, not necessarily the cutting structure failed. So if the bit balled up, that's where you look at your gamma ray and try to understand. But there is another very interesting computed channel that you can use, which is your depth of cut, which is normalized to your RPM. So it's the depth of cut, i.e. how far the bit cutting structure is embedded, normalized to RPM for one revolution. So, and that's the very easy computed channel to put in. And then always useful to look at depth of cut next to your weight on bit. That will instantly indicate to you that something is wrong with the cutting structure. Or there is a lithology change. Your gamma ray is not close enough to actually to know that.
All right. This one's from Maxim. Says #KeyDrill for our sponsor today. Thank you, sir. I'm more concerned is at what part of the world drill bits are not consumables, where the approach for drill bits performance is still has value for the customer. So is there any spots in the world? Oh, and he's back. Keep dropping out there, Vasiliy.
Yeah.
But all right. Is there any place in the world where drill bits are not consumables?
So this
Like
is
odd
this is a
question.
very so in the age of you know, very advanced materials and very you know, advanced modeling and etc. There is a trend to actually especially for larger sizes drill bits to be rentals. You know, something that is repairable, something that can be rerun. So in terms of value to the customer, it is a consumable generally, but you want that bit to be pulled out in one piece, and you know, even if it's not repairable, still in one piece. So you want to use the bit as per its design purpose. So in terms of repairability, there's one point actually I wanted to make. So why the repaired drill bits are never treated as new bits, or there is an understanding that the repaired drill bit is not as good as the new bit. This is partially correct, only because how the bits are repaired. So usually what is happening with repair, you know, you have a couple of cutters on the shoulder worn and everything else looks fine. So I remove the cutters on the shoulder. The properties of the cutter as the functions are the function of the number of heat cycles that it has been exposed to. So if you're changing that one worn cutter on the shoulder, the cutter next to it, which is in good shape, which was originally braced already first time around, is exposed to another heat cycle. So this cutter is no longer as good as it was. So when you repair a drill bit, and if you want the bit to be as new, you change all the cutters, no matter how they appear to be, because each heat cycle reduces the cutters. So the cutters before they were braced onto the bit, they're actually much better than they are when they are on the bit. So here we go. That opens up another kind of future development, right? Or alternative retention, or low temperature retention of the cutters. So, but
So
that's
cold
not
bracing?
answering. Well, again, you need to understand the properties of the cutters, at which point the heat actually damages the cutter. So you just need to stay below that point. I wouldn't call it cold, so you'd still burn yourself. But
Yeah.
without any heat, you know, there are several developments, and I've seen some patents on mechanical retention of the cutters. That brings a topic of rapid repairability. I mean, you should be able to repair the drill bits on the rig side. That would be ideal, wouldn't it? So, yeah, and once we get to rapid repairability, all of a sudden it's not exactly inconsumable. You would want to design the body of the bit and in such way that it doesn't fail. So you reduce the probability of that to fail. You remove things that fail in the design. So that, which is a big task, by the way, to do from the design perspective. That goes all the way to the core of your bit design philosophy. But once we get into rapid repairability state, which is inevitable, the consumables will be the cutters. The body will be the asset.
So it makes me think like you could just kind of go like this, and like all the cutters fall out, and a new set pop right in.
And that brings me to a very long future. You know, the adaptive cutting structure. The cutting structure that changes its properties based on the environment response. So that's a very long in the future. Well, again, I hope not too long. I still hope to see before I retire. But that's, you know, if the money is not a question, what do you want in the bit? I don't want to think about a drill bit, right? I want to pick up a solution, put it into the BHA, and know it works. That's ultimate what you want to do. Is the bit discussion ultimately should move from the technical aspects, you know, minute details, to commercials. You know, I want a drill bit to drill 1,000 meters. How much? You know, and you know it will drill it. But that's obviously taking it to completely different level, and we are not there yet, but we will be.
All right. Well, let me keep filing through on some of these questions. We got a bunch of them here. PDC bit design affects performance, but only when the bit is on bottom, engaged, and rotating properly. Insights from Utah 4 show most bit damage is due to BHA dysfunctions, resonance, bounce, and whirl. Your thoughts?
Correct. You are absolutely correct there, Robert. So we've seen Utah 4. In fact, some of the members of our company actually were involved in analyzing high-frequency data, and a lot of discussions about the BHA, the motor selection, the other aspects. And you are correct. You need to obviously design a drill bit that is suitable for this lithology, but the system behind it is as important. And that's why it's very difficult to isolate the bit performance from the rest of the string. So that's where the topic of instrumentation come along that I wanted to touch on. But yeah, so you are absolutely correct. The bit engineer, so you cannot select the drill bit without really understanding the system, without really understanding the BHA design, the drive types, what the drive actually does. You know, what's the difference between the motor and rotary steerable system, what the difference between push the bit and point the bit, position of stabilizers, properties of the mud, properties, well, the parameters that you use. It's very important. But the good thing, a lot of things can be modeled these days, and the modeling power and understanding of the modeling is actually improving. And in the future, big parts of it will be automated.
Excellent. All right, this was from Mohammed. What are the boundary conditions that you put in case of drilling high pressure, high temperature wells?
Well, so if you look at the PDC drill bit specification, right? Let's focus on PDC drill bits for now. The temperature is never specified there. There is a temperature limit though. So the first temperature limit comes from the nozzles or ports, because they use seals. So the seal temperature rating would be your limit, usually 220 degrees. If you're drilling a higher temperature, you just braze in the ports. So once you braze anything in, the temperature limitation of your braze becomes a limit. And it's not static temperature. You need to really account for added heat shock from the actual cutters cutting the rock. So, and it's usually 600, 700 degrees, probably more. Depends on the brazing, right? So, but yeah, it is much higher. But again, the temperature on the tip of the cutter gets really, really hot, and there is no clear understanding of how hot and at what conditions, and how CFD actually going to change that. That's where the next generation of instrumentation comes along. That's instrumenting each cutter with the thermocouple, you know, and record that data really to understand the heat profile generation of the drill bit as function of the parameters change. So, but that's in the future. I really hope it is now, but we are not there yet. The technology exists, right? Adapting this technology for downhole environment and also at cost, that's where the challenge is. And scalability is a challenge as well.
All right. Next question from Volker. I have a question. Intech are developing an RSS that modulates the under pressure at the drill bit to steer the drill bit direction. Do you have any views, positive or negative, on how that affects the drill bit stability and wear of a drill bit?
So are we talking about the preferential flow or preferential pressure on one side of the drill bit? If that's what we are talking about, it is a challenge. And in fact, we are involved in developing an understanding at this stage what the implications are. So the cutting structure is designed for concentric rotation generally, in most cases, unless it's a very, very special case where certain forces try to be accounted for. But if, let's say, you don't have that concentric engagement with the entire cutting structure, it will destabilize the drill bit. There are certain things that can be done from a design perspective, but they won't be to mitigate that instability, but to protect the bit when instability happens. And I think, give us a shout. I mean, I would love to talk to you about it in more details.
I just want to throw this comment up there when you were talking about it earlier. Somebody said volcanics granite 35,000 kpsi. Wow. So nice little comment there.
Yeah, easy done. 45 kpsi for PDC drill bits. I mean, we've seen, you know, the drill bits companies are pushing the boundaries way beyond 45 kpsi these days. And yeah, it's impressive.
All right. Next one, back to Maxim says, another question to drill bit folks. Are we overthinking and over designing drill bits? I mean, we cannot even manufacture a drill bit with very well precision. The difference in back rake angle from design model and build as build could be significant. The offset from the pin connection and the bit head could be significant to cause instability.
Over designing, so I'll take it from a different perspective. There is a lot of unnecessary complexities on a drill bit. They are sometimes to support some features that might or might not bring the value, or bring the value in a particular scenario which is very narrow. So in a grand scheme of things, is not value for money. So in that sense, yes, I think it is too complex. But also, we're talking about a lot of energy on such a small frame. But the manufacturing tolerances are constantly improving. Automation in manufacturing, machine learning is also constantly improving. There will be probably automation on either brazing or alternative retention methods in the future that will be much more precise. Precision is important because that's what drives the stability of the cutting structure. Is that always achievable? Probably not. But that's why the assessment of the performance is important. So why didn't the bit perform? Is that deviation from the design or deviation in manufacturing? So the drill bits companies do have tools at their portfolio to help to understand that. The bits are being scanned. It becomes commonplace these days. Pretty much every drill bit company you ask, they would tell you they scan the drill bits after it's manufactured. And the tolerances of acceptance becoming tighter and tighter pretty much every day.
Excellent. All right, next one here from Peach Holtzman. Peach, would love to have you on the show, by the way. Have you developed methodology to evaluate and model shaped cutters? If so, have you found any of the shaped cutters to reflect their stated benefits?
Oh my God, this is the best question so far. Sorry, everyone else. This is preceding my next week LinkedIn post, by the way. So we have modeled one shape to account for the shape in our forces modeling and the torque output and etc. It is already, so we pretty much went through a lot of testing and understanding how it actually reflects the reality. So I have to tell you that sometimes what the perception is of something hypothetical can be very different to when you model it. Yes, we see the advantage of a particular shape that we have designed into our cutting structure modeling software, and it does what is actually proposed for that shape, but to a much smaller magnitude. But more studies need to be done, so we're currently at the modeling stage, but empirical data will follow. Cutter shapes need to be modeled, included into the modeling. Cutter shapes are beneficial. in applications, depending on the shape. Not all the shapes are beneficial. I've seen some counterproductive shapes. And every time you shape cutters, you need to think about the implications of that and where in the cutting structure those cutter shapes actually placed and for what purpose. So shaping cutter usually affects some other properties of the cutter that are also important. So don't just go for any shape. But yeah, modeling is important, and it is happening, and we've done it already. So, and that's what we're supposed to be posting next week, unless Benoit tells me not to post it.
All right, one more from Francois. When making CFD simulation, do you have limitation regarding the RPM?
So RPM per se are not taken into consideration in CFD modeling. They can be, I think, to a degree. And also, if we're talking about RPM in terms of the heat generation, this is not a standard CFD package. So the temperature around the cutters can be modeled as well. That's a very different, that's another level of modeling. And perhaps one day it will become mainstream.
Okay. Next one here from Andrew says, if you could improve one body property, what would you choose?
Oh, why do I get to choose only one? So it's from Andy Bell. Okay, Andy, I'll give you the answer you will like. Erosion resistance.
I think he already knew that one was coming. All right, so Henry says, Vasiliy, you mentioned that bitware, as we all know, plays a very important role in the bit performance, but the software to predict bit performance does not take that into account. Would you please clarify this? I was under the impression there are bitware models which are built into bit performance software, so a full performance from the entire bit can be predicted.
There are attempts to do it. I'm aware of few. Again, to start with, right, each model that is currently in use will have some error model. This adds another complexity because, so when you say the worn cutting structure, so it wears gradually, right? It wears unevenly sometimes. It wears preferentially. So predicting that with any accuracy is extremely difficult. And getting any empirical data to confirm that is a big challenge. But things are moving that direction. It will become something that is done during the bit design phase. Yeah, I know there are several attempts to do it, and I'm not going to name company names. Some companies are more advanced than the other ones in that, but I wouldn't put my neck on the line saying that this prediction model actually correct. So.
All right. Well, that's the end of all the questions that we got from the audience. Vasiliy, anything else that you would like to be able to share with the audience today?
Well, the weather in Aberdeen is quite nice today, so which is a big surprise. But thank you very much for having me. It's always, I always wanted to be on the show. I didn't know that I will ever get a chance, but I was quite surprised. Thank you very much, and thanks everyone who tuned in, and all the good questions. Thank you very much as well.
Oh, well, hey, we got a couple more questions that have come in right here at the end of it. Okay. So then Henry says, agree, but wouldn't a bit of bitware built into the performance prediction better than nowhere?
Well, again, it depends. So if you might overpredict, that's the problem. So if you overpredict, you start over-engineering, and you know it can be kind of never-ending loop. But yeah, I think it's important to go with the facts, what certainly known to be the fact, and go from there. There are other secondary indications you can take while actually using your drill bit to say the bit is actually wearing. Another thing that is important to account for is to look at the cutter properties as themselves. So the cutter vendors will provide this information if you ask them nicely. So I'd rather look at that to a degree rather than have hypothetical prediction until it becomes robust enough.
Very well. Jonathan says, when you iterate the design of a bit based on performance, what data is the most important and helpful in achieving improvement? I think that's achieving.
Achieving. So as from Jonathan Prill. So Jonathan, I'll give you an answer that you will like. So the answer is, I of course want to know the stability of the drill bit with high frequency instrumentation, ideally, of course, on it. So, but yeah, the dynamics of a drill bit, which is derived from the total dynamics of a drill string, is a little bit of murky water, right? So instrumentation at the drill bit can be quite important in really making the right design decisions.
Which goes right into the final question of the day. What sensors would you like to see routinely in drill bits?
I want accelerometers, I want gyro up to, so for Francois, I want gyro for 2000 RPM because his turbines are obviously spin really fast. But so high frequency data, something in excess of, 500-600 probably hertz as a minimum. Temperature as well. Also, in the future, the pressure sensor will probably become quite standardized sensor on a drill bit because it's for hole cleaning, for understanding a lot of aspects of how the bit actually cutting the rock and in what volume. So.
All right. Well, this is great stuff. We've gotten Henry says, Vasiliy, excellent presentation. Andrew says, thank you. Great presentation. Franz says, it was a brilliant session. Thank you so much for your time. I says, muchas gracias for the stream and guests. And Gerard, thanks a lot for the quality of the presentation. Man, I hope all you guys keep
there was no slides.
Yeah, keep tuning into the show. Feel free to go to YouTube and watch prior episodes. Tracy is going through all of the old episodes and writing up show notes for everything, so you can quickly search for all of the notes and everything. Maybe at some point in time, we'll put all of that together into like one just giant PDF that you can kind of search through and look for notes whenever we're talking about certain topics. All right, I said it was the last question, but maybe we'll throw one more in here. Hi, Vasiliy. What do you prefer for extending bit life and vibrations, environment, downhole mitigation tools, or variation of RPM top drive?
I have no preference. I think it's application driven. Ultimately, I want the weight on bit to be consistent on a drill bit. Everything else can be designed around it.
There we go. Obviously, this is like,
yeah.
Sure. I mean, it's good for me. I mean, I'm not a drill bit guy. I don't know any of this stuff. That's why I have you come on the show, because I don't know any of these things. That's what I'm trying to learn. I'm trying to learn for free. I'm not going to pay for classes. I'm just going to invite people to come on the show. Nick says, first class, well done. Nice to hear someone talking about 150 mil drill bit. All right. Isabella says, thank you for the information. Robert says, great discussion and insights. Thank you, Celia and David. Peach, once again, I want to have you on the show. Great show. Thanks. Ian says, thank you, David and Vasiliy. Great talk. Thank you to KEYDRILL for bringing us today's show. Paul Moore says, thanks again. Great show. Excellent shows. Thanks, guys. And Eric, interesting points of view. Excellent. All right, we're not done yet. Everybody stick around for one more thing at the stage. Boom. There we go. All right, let's give away a drill bit and some KEYDRILL swag of some sort to be named in the future. So we'll hit draw, and we will see who the lucky winner is of today. Vasiliy, thank you so much for being on the show, man. Really, really do appreciate it. was an action-packed show. So it's Sion
Oh,
Roberts.
Sean Roberts. Hi, Sean.
Oh, Sean. Oh, okay. Sean is.
Yeah.
So, Sean,
Fantastic.
thanks so much for watching the show. Send me a message on LinkedIn. Give me your address, and we will get you a drill bit and some other KEYDRILL swag on the way. Thanks so much to KEYDRILL for stepping in and helping us to be able to put this show out there. Vasiliy, thank you so much. I look forward to your LinkedIn post about CFD, the good and the bad, or the before and after, whatever it's going to be. I'll look forward to seeing that this week. You guys tune in again next week. We will have no show. That's right. I've got a jiu-jitsu competition next week. So totally forgot about that. The week after that, though, we've got Andy Wood. I need to set somebody up for the 13th. And then the week after that will be Mike Barignac, who's going to be talking to us about oil field sales. Can't wait to be able to have him come on. Thank you guys all so much for joining us here. Really do appreciate it. It's been an amazing Friday. If you guys have any other questions, feel free to reach out to me if they're questions for me, or connect with Vasiliy on LinkedIn. He's very active. His company's very active, always putting out great content. So be sure to give him a like and follow. That's it for me, you guys. Everybody have an absolutely wonderful Friday. And as always, know your industry.